Good afternoon. Just picking up where we left off. Okay, and again we have working with the complex number system, and we have first of all, okay, I had given 5 problems to be looking at, and we're looking at simplifying where possible, and we have in the case of the first item. Okay, now we've got with the complex system ratio. Okay, so we got 3 plus 2i all over negative 2i and looking at working with what we have in the case of dealing with fractions in the complex number system. Okay, and again we had left off with conjugates, and in the case of dealing with what we have in conjugates, okay, so we got the denominator is negative 2i Okay, so you have the conjugate of negative 2i. It's going to be at 2i. Okay, and again we have at the crux, okay, for a complex number system, again I is in reference to the square root of negative 1. We have the I squared is equal to negative 1. And okay, and again for the standard form of a complex number, again we have a plus bi. And again, for the conjugate of a plus bi, we have a minus bi. Now, in looking at simplifying in terms of standard form, okay, we have, again, the ratio 3 plus 2i over negative 2i. And again, we can get this closer to standard form upon multiplying this ratio by 1 in the form of the conjugate of the denominator divided by itself. Okay, so just looking at what we have here. Okay, so you got 3 plus 2i over negative 2i. And if I multiply the ratio by 2i over itself, alright, so we have in the case of distributing, okay, so we got 3 plus 2i multiplied by 2i, so we have 2i times 3, so this will make 6i, and then we have 2i times 2i, so this will be 4i squared. And we have negative 2i times 2i, negative 2 times 2 is negative 4. And we have I times I becomes I squared. Okay, and again, I squared is equal to minus 1. So taking care of the squares of I. And we have in the case of the numerator, okay, so you have 6i plus what's going to be 4 times negative 1 in the denominator. I have negative 4 times negative 1. And looking at what we have now, so we got 6i minus 4. We have all over negative 4 times negative 1. Okay, so we have over 4. And we're getting closer to establishing what we have in standard form. And if I split up the terms, okay, so you have 6i over 4 minus 4 fourths. And these ratios can be simplified. Now 6 fourths is a fraction that can be reduced to 3 halves. Okay, so we'll have 6i over 4, we can write as 3 halves of I. negative 4/4 we have at -1. And then to write in terms of a plus bi, okay, if you notice your a value is going to be a -1 and your bi is going to be at 3/2 of I. And so we have for the official standard form for this complex number, okay, this will come out to -1 plus 3/2 of I. Okay, now for what we have in the next item, okay, we're looking at multiplying complex numbers, okay, and in this particular setup, okay, now we've got the quantity, okay, so we have 4 plus 2 times the square root of 7i. We have times the quantity, so we have 3 minus 3 times the square root of 7i. And so for what we have in this particular setup, okay, so we've got, again, two complex numbers. And if we look at multiplying these together, okay, and so we can FOIL out the products. Okay, so we have, for the first item, okay, so you have 4 times 3. Okay, so this will make 12. And then we have for the outside product, we have 4 times -3 square root of 7i. So you have minus 12 times the square root of 7i. And we have 2 square root of 7i multiplied by 3. So we have 6 times the square root of 7 times I. Now we have, in the case of the last product, okay, we have 2 times -3. At least for this part, we have -6. For the radicals, okay, we have the square root of 7 times itself. So we have the square root of 49, and we have I times I, okay, which is going to be at I squared. And gathering what we have now, okay, so you got 12 at the front, okay, and we have in the complex terms, all right, we have not just an I, but the square root of 7i, and the leading coefficients we have at -12 and +6, and if I combine, we've got -12 square root of 7i and 6 square root of 7i, so this will be -6 times the square root of 7 times I. Then for what we have toward the end, okay, have 6. Now we have the square root of 49, so this will be 7. And once again, we have I squared is going to be at -1. And looking at the follow through, okay, so about 12 minus, okay, we have 6 times the square root of 7 times I. And then we have for the constant product at the end, okay, we have -6 times 7, we have -42. -42 times -1 is going to be a +42. And so for what is going to form A will be the sum of 12 and 42, which will make 54. And the BI term is going to be the negative 6 times the square root of 7 times I. And that will be the final result for this one. Alright, now for what we have in the case of the third item, okay, so this is another run-in like number 1, okay, and in number 3, okay, so we have a fraction that is in the form of 2 over 3 minus 5i. And I want to put this in A and BI form. Okay, and okay, so we have with the denominator. Okay, so you have 3 minus 5i. And the conjugate of the denominator. Okay, is going to be 3 plus 5i. So looking at what we have now, okay, so you've got 2 over 3 minus 5i. And once again, multiplying this ratio by the conjugate of the denominator over itself. Okay, so 3 plus 5i over 3 plus 5i. And for what we have upon distributing, okay, so in the numerator we have 2 over the quantity of 3 plus 5i. So we have 6 plus 10i. And for taking the product of what we have in the denominator, and again, the product of conjugates is going to be a constant. Okay, so right now 3 times 3 is 9. Now you're going to have the outside and the inside products to cancel each other, since we're going to have respectively positive and negative 15i. And for the last product, okay, so we have negative 5 times 5 is negative 25. I squared and carrying forth what we have. Okay, so right now we got 6 plus 10i, and we have in the denominator, okay, so I have 9, and again the first order I terms canceled out, and we got minus 25, and for I squared, okay, I have negative 1, okay, and as we're drawing nearer, okay, so we got 9, negative 25 times negative 1, okay, so this will be a plus 25. Okay, so I have 6 plus 10i over 34. And now looking at splitting up, to get to the official a plus bi form. Okay, so we have 6 over 34, which can be reduced. And we have also, for the complex variable term, we have 10/34 of I, and this ratio can also be reduced. And so for 6 over 34, okay, we have a ratio of even numbers, and 6 over 34 can be lowered to 3/17. And for 10/34 of I, have another ratio of even values, and 10/34 of I is reducible to 5/17 of I. So you have the A at 3/17, and BI we have at 5/17 of I. Now, for what we have in the case of, okay, the fourth item, now we're looking at complex radical terms, and looking at what we have here in this particular array. All right. Okay, so I have the square root of negative 72 plus the square root of negative 98, okay, and we have plus the square root of 25, and we have minus the square root of negative 800. And looking at what we have for this quartet, okay, so we're looking at trying to convert this sum to where we can combine like terms and write in a plus bi form, where is possible. Okay, and in the case of working with complex radicals, okay, again, we're going to factor out the I. Again, I is in reference to the square root of -1. Okay. And we have just the square root of 25, and we can go ahead and write that as 5. All right. Now, with the I terms, okay, we have with these radicals, none of these are perfect squares, but they are multiples. Perfect squares greater than 1. Okay. Now for 72, okay, we have among the perfect squares besides 1, we're going to have like 4 will go into 72, 9 will go into 72, and also you're going to have the highest perfect square divisible into 72, and that will be 36. Now for 98, not a perfect square, but the multiple perfect squares greater than 1, and the highest number, okay, like in this case, that will go into 98, and that will be a perfect square. We have 49, and 49 will go into 98 2 times. So again, we're factoring, so we have the square root of 49 times the square root of 2 times I. Again, just bring down the 5. And we have next in line, we have with the square root of 800. Okay, not a perfect square. There it is, the multiple of perfect squares. Now the highest perfect square divisible into 800 will be 400. And 400 will go into 800 2 times. And looking at what we have in reduced radical form among the complex terms. So for the square root of -72, okay, this will come down to 6 times the square root of 2 times I. For the square root of -98, okay, this will lower to 7 times the square root of 2 times I. We have plus 5. And we have minus. Okay, now the square root of 400, okay, that would be 20. We have times the square root of 2 times I. Okay, so we have only one term that is a standalone constant. Okay, and that's with 5. And if we assemble the complex terms, and if you see the sum for the complex terms already, that's fine. Okay, so representing A in this case, we're going to have it 5. And then we have for the complex terms, okay, notice you have what makes them like terms is not just that we have I, but the square root of 2I. And so if we combine the leading coefficients, so we have 6 plus 7 is 13. In turn, okay, 13 minus 20 becomes -7, and it's going to be -7 of what? And it will be with the entities that make these last 3 terms like. Okay, so we have the square root of 2I, and for your A and BI combination, okay, we come out to 5 and -7 times the square root of 2I. Now, for what we have in the case of taking the product of complex radicals, okay, and here we have in this array, all right, so we have negative square root of 2, we made that square root of -2 times the square root of -6 and then we have times the square root of -3 and we have times the square root of -4. Okay, And there are separate pathways you can go about solving. Okay. And we'll go ahead and write all of these, okay, since they are all complex radicals. We'll put these in terms of I. So we have the square root of 2i times the square root of 6i followed by the square root of 3 times I and have times the square root of 4 times I. Okay, so all the numbers inside the radical are positive upon extracting the representation of the square root of -1, which we have in the letter I. Okay. Now, again, there are different routes you can follow through on in terms of arriving at the solutions. Now, let's say that if I look at like just pairing up the first two terms, so I have like the square root of 2, square root of 6, I times I becomes I squared. If I do the last two terms, okay, so I have the square root of 3 times the square root of 4, and I times I becomes I squared. Okay, so square root of 2 times the square root of 6. We'll just cluster these numbers together. Okay, so I can multiply square root of positives, but I could not do it in case of multiplying the square roots of negatives. Okay, so we have the square root of 12. I squared becomes -1. Again, we have the square root of 3 times the square root of 4, so we have another square root of 12. And I squared we have at -1. And I'll just rearrange the factors. So you got in the radicals. So you got the square root of 12 times the square root of 12 you got -1 and -1, and -1 times -1 is just going to be 1. Okay, so we got these two. Okay, so have the product. Square root of 144, -1 times -1 is just 1. And so we have the square root of 144, and with 144 as a perfect square, this will come out to 12. All right, so we have further applications along the lines of working with complex radicals. All right, now heading back to what we have had with equations that have exclusively complex roots. We can take just as examples here. Okay, so if I have something like x squared plus 9 is equal to 0. Okay, now let me mention something. Okay, now when we first looked into what led to the zero product property, like we had a difference of squares, like x squared minus 9 is equal to 0, I could factor the x squared minus 9 into binomials x plus 3 and x minus 3. But for a sum of squares, I cannot readily factor into two binomial expressions with integer coefficients. And for x squared plus 9, okay, one might be tempted to say, well, would that not be the square of x plus 3? Well, if you try to say that the square of x plus 3 is x squared plus 9, here's the problem. Okay, now the square of x is x squared, and the square of 3 is going to be 9. But if I take x plus 3 times itself, I'm going to have x squared plus 6x, namely the sum of the outside and inside products, followed by the addition of 9. So because I'm missing the 6x, I cannot factor this as the square of x plus 3. So in terms of any recourse, in terms of what to do for x, what I can do is separate the x squared from the 9. And so I can just move the 9 over by subtracting. And so I have x squared is equal to -9. And for what I have here, so got x squared is equal to -9. And we have with the square root property of equality. Okay, so if I have like x squared set equal to a constant in this time where we are in the complex domain, and say that x is equal to plus or minus the square root of -9. You get square root of -9. You can go ahead and get to the final results here, but you got square root of 9i, and the square root of 9 is going to be at 3. So we have x, okay, we have plus or minus 3i. So this is a quadratic equation where we have only one appearance of x, where we have x squared. And let's say that if I have a couple of appearances in x in a quadratic, and let's say if I have x squared plus 6x plus 25, okay, is equal to 0. Now we have a quadratic equation that is set up in standard form. Okay, now if I tried to factor this trinomial, okay, again, now you could say x squared goes to x and x, but the problem will be with the last two coefficients. If I think of two numbers that will multiply into 25, like 25 and 1, 5 and 5, neither combination will add up to the middle number, which we have in 6. Okay, so I cannot do the direct factoring and then solving by the zero product property. But again, we have as a pathway to nonetheless solving, and this will be with, once again, the quadratic formula. Okay, so I got for x squared. Okay, any other way to read this is 1x squared. Okay, so we have a is equal to 1, and for 6x, so I have that b is equal to 6. And we have that c is equal to 25. And so for the quadratic formula setup, again, we have negative b plus or minus. And we have the square root b squared minus 4ac all over 2a. Okay, and then crossing over to the substitution stage. Okay, so you have a negative b. Okay, so you have negative 6 plus or minus. Inside the radical, so we have b squared becomes 6 squared, and for minus 4ac, so I have minus 4 times 1 times 25. We have all over 2a, so we have 2 times 1. Okay. And after the substitution stage, okay, so you got 6 squared again. That's going to make 36. Negative 4 times 1 is negative 4. And then we have negative 4 times 25 is going to be negative 100. And we have over 2 times 1, which will be 2. All right. So we have, in the case of the square root of 36 minus 100. Okay, now the difference inside the radical, we have it negative 64 And for the square root of negative 64, and we have the square root of 64 times the square root of negative 1. And so this is going to go to the square root of 64i. And the square root of 64 is going to be 8. And multiplied by I, so the square root of negative 64 is going to be at 8i. Okay, so we have negative 6 plus or minus 8i all over 2. And we have upon branching out. Okay, so we have negative 6 over 2, and we have 8i over 2. Okay, and so we have even valued leading coefficients. Okay, so say we have 2 will go to negative 6, negative 3 times. And we have plus or minus. We have 2 will go into 8i, 4i times. And then we have in separating, we're going to have negative 3 plus 4i. That's one solution. And then we have for the other, we're going to have negative 3 minus 4i. All right. And I'll tell you what, in looking at solving for x, so just for the next few moments, let's see what we get for x when we have 3x squared plus 48 is equal to 0. And also where we have x such that 2x squared plus 3x plus 2 is equal to 0. So let's see what complex roots we get for these items. Okay, so we've got 3x squared plus 48 is equal to 0. And okay, so if I isolate the variable term, okay, so we have upon taking 48 away from both sides, and let me pause again. Now you could have factored out 3 and then divide by 3 the whole equation. But if I just isolate the x squared term, okay, we have 3x squared is equal to negative 48. Okay. So in other words, I can divide and then isolate, or I can isolate and then divide. And regardless of whichever pathway you choose, you're still going to come out to x squared is equal to negative 16. Okay, so take away 48 divided by 3. So you have the x squared is equal to negative 16. And we have with the square root property of equality, so we have the x is equal to plus or minus the square root of negative 16. Now while the square root of 16 is 4, that of negative 16 is going to be 4i. Okay. So we have for x, we have plus or minus 4i. Okay, so in this case, okay, we have 2 complex roots. Now, for what we have in the case of the next item, okay, so we have 2x squared plus 3x plus 2 is equal to 0. And this almost looks like a trinomial you can factor, but it doesn't quite pass muster in terms of integer coefficients. And you could think of factoring by grouping, like multiplying 2 and 2, which is 4, but there are no integer factors of 4 that will add up to positive 3. You might think of like 4 and 1, which will add up to 5, and the other combination that's positive will be 2 and 2, but that adds up to 4. So there are none that will add up to 3. And so if we look at the quadratic formula. Once again, so we have a at 2, which is in reference to 2x squared, and we have that b is equal to 3, and for the constant at the end of the trinomial, okay, that, like a, is equal to 2. And looking at reapplying, okay, the quadratic formula. Okay, so for negative b, okay, we're going to have minus 3. Plus or minus the square root. Now b squared will become 3 squared. Minus 4ac, we have minus 4 times 2 times 2. And we have all over 2a, which will be at 2 times 2. Okay. So again, the only thing I've done at this stage is substitute. And looking at what we have and following through. So we're going to have negative 3 plus or minus. We got the square root. Now 3 squared is 9. Negative 4 times 2 is negative 8. Negative 8 times 2 is negative 16. And we have all over 4. And we now have 9 minus 16. Okay, so we have negative 7. And again, whenever you have the square root of a negative, put that in terms of I. Don't leave it as just the square root of a negative. Okay, so this, in this case, we're going to have the square root of 7 times I. And if I had to put this in a plus bi form with our solutions, so if I break up, we're going to have x is equal to negative 3/4 plus the square root of 7 all over 4 times I. Now the other end, we'll have negative 3 minus the square root of 7 I all over 4 translates to negative 3/4 minus the square root of 7 over 4, and we have times I. All right, so these are going to be our solutions, and again we have complex roots. And for what we have in the case of just the kind of some of the held over book problems, and we had from section R.6, and among the items, okay, we had in number 68, okay, and we have solving for a different variable. Where we have in number 68, okay, we have the letter at m. Okay, and here we have for this equation, we have m times the quantity of m plus 10 is equal to negative 34. And again, the temptation might be to set each of these factors equal to negative 34, but you cannot do it that way. Okay, if you were to set equal to, the constant to the right has to be 0. Okay, so you cannot use the zero product property if the constant on the other side, the equal sign, is non-zero. So in terms of working with m, okay, so you had to work around this. So we can break up the factored notation upon distributing m over the quantity of m plus 10. Okay, so we have m squared plus 10m is equal to negative 34. And okay, so you have a quadratic equation in the variable m. And if I take this equation and put in standard form and have the right hand side at 0, I'm going to add 34 to both sides. Okay, so we have m squared plus 10m plus 34 is equal to 0. And again, just for this trinomial, okay, if you try to factor, the thing is, the factors of 34 that are positive, you have 34 and 1, they add up to 35. Other combination is going to be 17 and 2, and those numbers add up to 19. So no combination will add up to 10. Okay, so a bit of history repeating. It's a different letter we're solving for, but we still have setting up A, B, and C to establish the quadratic formula use. Okay, so we have the A is equal to 1. And we have the B is equal to 10. And we have the C is equal to 34. So we're going on the same premises, this time solving for M as opposed to X. Okay. So we have for negative B, we have negative 10. We have plus or minus the square root. Now for B squared, we have a 10 squared minus 4AC. We have minus 4 times 1 times 34. We have all over 2A, so we have it 2 times 1. And expanding, okay, so we have negative 10 plus or minus. Okay, now we have with the square root. Okay, so 10 squared is going to be 100. For the minus 4AC combination, negative 4 times 1 is negative 4. Then we have negative 4 times 34 is going to be a negative. Then we have minus 136. We have all over 2. And gradually getting this down where we will ultimately be able to reduce. Now we got 100 minus 36, so we have the square root of negative 36. And we have the square root of negative 36. The square root of 36 is 6. That of negative 36 is going to be a 6i. So you have this combination, negative 10 plus or minus 6i to be divided by 2. And I can reduce negative 10 halves becomes negative 5. We got plus or minus, and 6 halves of I becomes 3i. So this is our clustered solution, and separating. We're having in line with the Alex notation. We're going to have negative 5 plus 3i. Also we have negative 5 minus 3i. And so those would be the complex number solutions for what we have in M. Now, for what we have in the case of 71, these problems, or this problem rather, is kind of akin to the first two items we looked at yesterday, and where we had like a single variable term plus a constant set equal to 0. Okay, but in those other two problems, now the coefficient of the variable term happened to be a number completely factored or factorable into the constant that was added. Now here we have an exception. Okay, now we got 9x squared plus 49 is equal to 0. So 9 will not go completely into 49. But like the other problems, I can still isolate the variable term 9x squared by removing 49 upon subtracting. Okay, so we have 9x squared is equal to negative 49. And then we have looking at getting in terms of x squared. So looking at dividing by 9. Okay, so I have 9x squared over 9. So this will be x squared So x squared is equal to negative 49 ninths. And we have with the square root property. Okay, so if I go from x squared to x is going to be equal to plus or minus the square root of negative 49 ninths. Now, just mention, just kind of step over to the side here. So you got the square root of negative 49 ninths. Okay, again, 9 does not go completely into 49. Right now, I've got the square root of 49 ninths of I. Okay, however, in terms of square roots, guess what? 49 and 9 are both perfect squares. Square root of 49, okay, this will be 7. Square root of 9 is going to be 3. And guess what? The square root of negative 49 ninths comes out to 7/3 of I. And so we have from the square root property of equality, okay, so you have x is going to be plus or minus, where we had the square root of negative 49 ninths to be 7/3 of I. And so we're back to where we have single term additive inverse solutions for x. Okay, so I have x equal to negative 7/3 of I, as well as positive 7/3 of I. So in terms of solutions, there are a lot of parallels drawn with the earlier sections, okay, like especially those that involve the zero product property, the quadratic formula, and also the square root property of equality, but where we have exclusively complex roots. And now we're going to have for those equations that can have a blend of real and complex roots, these are going to be what are referred to as equations quadratic in form. And for what we have in the case of equations quadratic in form, okay, it's going to be a little bit of a lengthy definition, but you'll see a pattern that will follow. Okay, so I have equations quadratic in form will be equations where if there are two terms, not that there will be two terms, but if there are two terms, and the dependent variable okay, so you have equations where if there are two terms in the dependent variable, the higher degree term will be twice the lower degree term. And just samples of equations, quadratic in form. Now, they might look like quadratic equations, and I guess in a sense they are, but we're looking at other degrees as well. And let's say that if we have Okay, just samples of equations, quadratic in form. And we're not solving for x or whatever variable is involved yet. We're just taking a bit of sample, a bit of sampling. Okay, and we have, let's say, a case could be, let's see, dependent variable, yes. Yeah, in other words, that's the variable you're solving for. Okay, so if I have like x to the fourth plus 19x squared, and we have plus 1 is equal to 0. Okay, so I have x to the fourth plus 19x squared plus 1 is equal to 0. Okay, and if you notice, we have two variable terms. Okay, so I have x to the fourth. You also have x to the second. And if you notice, in the ratio between the higher order and the lower order terms, you have like a 4:2 ratio in the degree nx. So for this equation, okay, this is going to be said to be quadratic in the lower degree variable factor. Okay, so we can say that this equation is going to be quadratic in x squared. Now let's say that as another case here. If I have like 3 times x to the 6th minus 97 x to the 3rd, going to have followed by the addition of 4 is equal to 0. Okay, so we've got two variable terms, and the higher degree term will be twice the lower degree. So here you have like, so you got like 6 to 3. You have like a 6 to 3 ratio. Okay, that's a 2 to 1 ratio. And this particular equation will be said to be quadratic in x cubed. So that's going to be quadratic in the lower degree appearance of the variable x. Right. And this doesn't have to be just integer powers. I'll give you a situation here. If I have, let's say, 5x minus the square root of x plus 88 is equal to 0. And another way to write this, okay, remember, we're just working with radicals time and again. And when we looked at, say, non-integer exponents, okay, like the square root of an expression is like that expression taken to the 1/2 degree. And so you could say that just for 5x, you have 5 times x, or 5 times x to the first. Okay, so you have x is a first degree, and we have the lower power in x. Okay, we have at 1/2 and a 1 to 1/2 ratio. So if you divide by a fraction, it would be the same as multiplying by that fraction's reciprocal. Okay, so you still have in proportional terms, we got a 2 to 1 ratio, and so for this particular equation, you say this equation, you can say it's going to be quadratic in the square root of x, or as its exponential equivalent, we could say that it is quadratic in x to the 1/2. And okay, so for these, okay, so for equations quadratic in form, okay, now they could be just single variable equations. Okay, but if you have two variable terms, okay, again, the higher order variable term would be twice the degree of the lower. And these three cases are as such. Now, in the case of looking at equations quadratic in form, where we can be solving for x, not these problems, but something that will be more factor friendly. Okay, say if we're looking at solving for x, and we have, let's say we have x to the fourth plus 3x squared minus 4 is equal to 0. Now we have a polynomial expression, and let me just kind of mention something here. You got with the number 4, we're solving for x, and the highest degree appearance of x is 4. And now for what that 4 can signify in terms of what you might anticipate, you can have possibly, there's no guarantee, but possibly that many solutions, like possibly 4 solutions if the equation is a conditional. Again, conditional as in where you're going to have solutions, but a limited number of solutions. Otherwise, you might have at the extreme an infinite number of solutions if we just happen to have an identity, or we might have no solution if there's like trying to say that two sides are equal to each other when they cannot be made equal. Right, and we have for this equation, so you have x to the fourth plus 3x squared minus 4 is equal to 0. And again, so you have this running, you have like a 4:2 ratio, and you don't have to identify every time what the equation is quadratic in. But again, we have this equation to be quadratic, in x squared, and just looking at what we have here. So what does that mean? Well, in terms of what the equation is quadratic in, if we have the coefficients to be just right, where I can factor into binomial expressions. Okay, so x to the fourth, we have quadratic in x squared. Since x squared appears as the lower degree variable term, so that means I can factor out x to the fourth as x squared and x squared. And for the factors of -4, whose sum or difference will be on the plus side at 3. So this will signal that more weight is given to the addition than to the subtraction. And again, you can check x squared is x to the fourth. And then we have outside product is -x squared. Inside product we have 4x squared, combining -x squared and positive 4x squared. So we have 3x squared, and then we have 4 times -1 is -4. And now again, I'm going to look at factoring where I can, even though factoring at this stage is optional. Okay, now x squared plus 4, that's the sum of squares. This cannot be factored into real integer terms. However, for a difference of squares, like in the case of x squared minus 1, we can factor out to x plus and x minus 1. And we can now utilize the zero product property. So if I set each of these factors to 0, right, and just for the quick answer portions, okay, if x minus 1 is 0, we've got x is equal to 1. If x plus 1 is 0, we have x is equal to -1. Now for the sum of squares that we have with x squared plus 4, I'm looking for solutions, so I can take 4 away from both sides. So we have the x squared is equal to -4, and we're back in the terrain of the square root property of equality. So I can say that x is equal to plus or minus the square root of -4, and square root of 4 is 2, and again that of -4 is going to be at 2i. Okay, so we're going to have 4 solutions in x. Okay, so you have 2 are going to be in the complex domain with -2i as well as 2i, and the other 2 are from the real number system where we have -1 as well as +1. All right, now for what we have for an equation quadratic in form, but where you might have the variable to appear only once, and this would be like when we looked at the first bit of factoring. You had your trinomials to factor, you have like these other entities to be like the difference of squares, where you had the variable x to appear one time. And for a case here, like for an equation that is quadratic in form where the variable appears once, and I'm going to keep this in 4th degree as well, we might have a difference of squares in another sense, whereupon we have x to the 4th minus 81 is equal to 0. And for this one, for x to the 4th, just like earlier, okay, that times itself, that will give you x to the 4th is going to be x squared and for minus 81, okay, you see we have x squared minus 9 and x squared plus 9. And again, for the difference of squares, you can factor. So you have x plus 3 times x minus 3, and x squared plus 9, this stays. And now looking at the zero product property at this stage, okay, so you have x plus 3 is equal to 0, we have x minus 3 is equal to 0, also you have x squared plus 9 is equal to 0. So once again, if x plus 3 is 0, and I'll isolate this x, taking away 3, so we have x is equal to -3. If x minus 3 is equal to 0, okay, so I can isolate x by adding 3, so we have x is equal to 3, and for x squared plus 9 equal to 0, if I take 9 away from both sides, so I have that x squared is equal to -9, and then lowering from 2nd to 1st degree, so we have that x is equal to plus or minus, okay, the square root of -9, and I'm going to have the x equal to plus or minus 3i. Okay, so we have in this setup, okay, it's not always as such necessarily, but I do have another 4 solutions where I have 2 real numbers with negative and positive 3, and then we have the complex numbers with 3i and its additive inverse -3i. Alright, now, so this is a sampling of equations quadratic in form, and it does open a potential pathway for there to be both real and complex roots, okay, and it might have both categories, or it might be limited to just only one type. And now let's say that if we have, I'll show you just a case here, just kind of relate how the coefficients are going to be aligned. I'm going to kind of change up the degrees a bit. Okay, so it's kind of like going back to the looking at solving a quadratic equation. Like if you have like x squared plus 4x minus 32 is equal to 0. Okay, so this is a quadratic equation. And we had the coefficients whereupon we can factor it. So x squared will go to x and x. And factors of negative 32 whose sum or difference will be on the plus side at 4. So we have more weight given to the addition than to the subtraction. Okay. So we got the quantity of x plus 8 times that of x minus 4 equal to 0. And if we have x plus 8 equal to 0, where we're going to have that x is equal to negative 8. If on the other hand, I had the x minus 4 is equal to 0, where we're going to have that x is equal to 4. Now let's say if I keep the coefficients and I take an equation that is quadratic in form. Say instead of x squared, I'm going to go with x to the 4th once again. So I have x to the 4th plus 4x squared minus 32 is equal to 0. And just as x squared factors out to x and x, and we'll have x to the 4th will factor out to x squared times itself. And again, factors in negative 32 whose sum or difference will be at 4. I can have this bit of history to repeat. So I have x squared plus 8 and x squared minus 4. Now x squared plus 8 I cannot factor into integer coefficients, but now with x squared minus 4 I can factor this difference of squares in real terms, where I have x plus 2 and x minus 2. And so I got 3 factors here, and if I set each to 0, okay, so I have for x squared plus 8 equal to 0. Okay, so if I take 8 away from both sides, so we have x squared is equal to negative 8. And going from x squared to x, so we have equal to plus or minus the square root of negative 8. And just doing some gradual lowering here. Okay, so for the square root of negative 8, we have the square root of 8i. Now again, 8 is not a perfect square, but its square root can be reduced. And so we're going to have for x in this capacity case, so you have plus or minus. Square root of 4 is 2. You have times the square root of 2 times I. Okay, so we have 2 complex roots. As for the other factors, we have x plus 2. If I set this to 0, okay, so you have x is equal to negative 2. And if x minus 2 is equal to 0, so we have that x is equal to 2. Okay, so we have 4 solutions once again. So we have x is equal to negative 2 times the square root of 2 times I, as well as 2 times the square root of 2 times I. And again, we have with the real number solutions, okay, we'll have it negative and positive 2. And for what we have, say just as a remaining case, and just kind of running in tangent or tangently, okay, to this quadratic equation I started out with, and I said that I would change up the degree. And for this remaining example, Okay, let's say if I had x, just x, and I have plus 4 times the square root of x minus 32 is equal to 0. Okay. Now again, this is a case kind of like what we had earlier. We have like x, square root of x, and the equation is quadratic in the square root of x. Okay. Now we have with this expression, I can factor x into the square root of x times itself. Okay, so for the x, if I factor, then we'll have the square root of x and the square root of x. That's right, just kind of backtracking here. So x squared I had to factor out to x and x. X to the fourth had x squared and x squared. Now for x I have square root of x and the square root of x. And guess what? I'm going to have the same constant combinations. Plus 8 minus 4. Plus 8 minus 4. Once again we have plus 8 and minus 4. And we have with these factors, both of these as radical equation setups. Okay, so if I set the square root of x plus 8 equal to 0, as well as the square root of x minus 4 is equal to 0. If I look at isolating each of the square root terms, okay, first of all, by subtracting 8 from the first setup and then adding 4 on both sides in the second. So for the square root of x plus 8 equal to 0, if I have the square root of x is equal to negative 8, guess what? For this part, I can stop because here we have an even root radical, and an even root radical expression cannot reduce to a constant that is negative. So there's no x such that its square root is equal to negative 8. And one might say, well, what about 64? Well, the square root, while negative and positive 8 square out to 64, strictly speaking, the square root of 64 is 8 and only 8. So for this part, we have no solution, and that's because of the principal square root rule. Now we have, on the other hand, with the square root of x minus 4 equal to 0, adding 4, so I have the square root of x is equal to 4. Now I've got a square root expression set equal to a positive 4, and the principal square root rule does allow that. So I can follow through and solve for x, and we have upon squaring both sides. Okay, so we have the square root of x squared. Okay, so that is going to be x, and 4 squared is going to be 16, and this is going to be our only solution. And just upon doing, say, like a quick double check, now again we have x is at 16, so if you were to plug in 16 back to what we have here, now the square root of 16 is 4, square root of 16 is 4, 4 times 4 is 16, first term x is 16, so you got 16 plus 16 is 32, and we have in turn, okay, 32 minus 32 is equal to 0, so this equation has only one solution.